Hello everyone, my name is Anitta Kurian, currently pursuing Master of Computer Applications from Marian College Kuttikkanam Autonomous. Today, I am delighted to present the topic Application of Graph Theory in Deadlock. So, without further delay, let's dive into the fascinating world of graph theory and its application in Deadlock. The overview of my presentation. We will cover introduction, the role of graph theory in deadlock, deadlock detection and prevention, real-world applications, advantages and limitations of graph theory. Finally, we will conclude with key takeaways. So, let's start with understanding what a deadlock is. A deadlock occurs when a group of processes are waiting for resources indefinitely, preventing further progress. For a deadlock to occur, four conditions must halt simultaneously. Mutual exclusion. Only one process can use a resource at any time. Halt and wait. A process is holding one resource while waiting for others. No preemption. A resource cannot be forcefully taken from a process. Circular wait. A circular chain exists where processes are waiting on each other in a loop. These conditions form basis of deadlock scenarios and understanding them is crucial for prevention and detection. Now, let's explore the role of graph theory in addressing deadlocks. Graph theory provides a vision and a mathematical way to model system resource allocations. In this representation, nodes represent process and resources, edges represent resource requests or allocations. This graphical representation helps to analyze and detect dependencies that can lead to deadlocks. One key concept in graph theory is the resource allocation graph. A resource allocation graph that shows resource allocation and request in a system. It consists of nodes and edges. Nodes representing processes and resources, and edge has two types, a request edge and an assignment edge. A request edge indicates a resource request and assignment edge indicates a resource has been allocated. For example, if we have two processes P1 and P2 and two resources R1 and R2, the graph will depict how the resources are allocated or requested by these processes. We use graphs to detect deadlocks. In a resource allocation graph, a cycle indicates a potential deadlock. For example, P1 requesting R2, R2 held by P2, and P2 requesting R1, R1 held by P1 forms a cycle and leads to deadlock. Algorithms like depth first search are used to detect cycles and helping us to identify deadlock conditions. Now, let's talk about how graph theory can prevent deadlocks. First one, eliminating circular wait. By assigning a numerical order to resources and ensuring that processes request resources in ascending order, we can avoid cycles. Dynamic resource allocation. The system avoids granting requests that would result in a cycle. Safe state. By using Banger's algorithm, we ensure that resource allocation leaves the system in a safe state, preventing deadlock. Let's move on to real-world applications of graph theory in deadlock detection and prevention. Operating system. Graph theory is used to manage multitasking and detect process resource dependencies. Databases. Deadlocks during concurrent transactions are detected using wait for graphs. Distributed system. Inter-process communication and shared resources in distributed systems are modeled using graphs. These practical applications demonstrate the significance of graph theory in solving real-world problems. Graph theory offers several advantages. Visualization. It simplifies the understanding of resource dependencies. Efficient detection. Algorithms like DFS can quickly detect cycles. Prevention. It helps in designing systems that avoid unsafe states and minimize deadlock risk. Despite its advantages, graph theory has some limitations. Complexity in large systems. As the number of processes and resources increases, resource allocation graphs become complex and harder to analyze. Real-time overhead. Continuously monitoring and updating the graph can be computationally expensive, especially in dynamic systems. In conclusion, graph theory provides a powerful framework for detecting and preventing deadlocks. Resource allocation graphs enable us to visualize and analyze process and resource dependencies. By detecting cycles and designing systems for safe states, we can effectively manage deadlocks. Understanding and applying these concepts is essential for building efficient and reliable systems. Thank you all for watching my presentation on application of graph theory in Deadlock. I hope you found it helpful and informative.